Okay. So we were saying that because f of 125 is negative is positive, while f at 200 is negative, then the new bracket will be 125 200. Okay, is it clear for the person who asked about it? It is clear.
Yes, doctor, clear.
Okay. And you will repeat this procedure until reaching a satisfying convergence criteria. Okay. Now, what is good about the bracketing?
دكتور
Yes.
بيكون الجراف given.
uh, graph function. No, ما بيكون given. Okay. هلا أنا just it's a method. Sometimes a method to know approximately where we have root is to draw the graph. بس كمان to you need to have several points. يعني ديجا بدك you should compute at several points. This will take time كمان. Okay.
يعني ما بتجيبينا الجراف ونحن نلاقي الروتس من ورا الجراف ونرجع نحله حسب
No.
المثل.
No, he just إذا بدكم it's a possibility بس numerical technique because we want high accuracy. I will not give you the graph. I just give you the initial bracket and you will proceed.
اوكي.
Okay. So now, if you remember, we talked about several types of errors in the chapter 4. And we said that one of the types we will define it in future chapters, the whole absolute error. When we say absolute error, we said it means it is the maximum possible error we can have. And this types of error is included in bracketing methods. Why? Because look, whenever you know that your root is somewhere in this bracket, already you have a certain margin for error. The maximum possible error that you can have in estimating the root will be the length of your interval, okay, which is x upper minus x lower. So this is for any bracket you have, okay, at any stage you are, you can say that the absolute error is equal to the length of the bracket. So to start with, even before doing any iteration, already your absolute error is equal to xu minus xn. You cannot have a larger error, okay, because already I am sure that the root is in this bracket as long as f at this end times f at this end is negative. Okay, so and this error will be reduced, of course, as I proceed, because as I proceed, I will divide by my interval by 2. Each time I do a new iteration, I'm dividing by 2 again. So when you do your first iteration, already your absolute error is divided by 2. When you do your second iteration, you divide again by 2, so it will be initial delta x over 2 squared. And you can develop a general relation that the absolute error at iteration n will be equal to delta x over 2 to the power n. This means that you can compute how many iterations I need to reach a certain absolute error without having to do all iterations. Okay? So for example, if they ask you, if I start from a bracket, let's say 2 to 5. So the initial absolute error is 5 minus 2 equal to 3. Okay? So E0A will be equal to 3. Then I can tell you I want to reach an absolute error of 0.1. How many iterations do I need? All you have to do is to do this equation. Why? Because look, if you just say, I want this error to be equal to a certain value, E desired, absolute error desired, and you want to solve for the value of n, all you have to do is to do ln from both sides, because 2 to the power n, ln or log, both will work, okay? 2 to the power n is equal to delta x over delta x0, which is the length of the initial interval, over the desired error, which is given, okay? And then if you apply ln to both sides, you know that ln 2 to the power n is n ln 2, Okay, so you get n ln 2 is equal to ln of delta x over e desired. So delta x at stage 0, of course. So you can get now that n is, it will work for ln and log, for both it will work. So n is log delta x over e over log 2. Okay, and in this way you can compute what is the number of iterations that will be needed to reach this absolute f. We will take example on this. If I go back to the same example we have done together, we started from an interval that the mass should be between 50 and 200. So what is delta x0? Delta x0 is the length of this interval. So all I have to do is delta x is 200 minus 50. It's 150. And the desired absolute error to reach is 0.01. So I should be lower or equal to 0.01. So all I have to do is to replace in this formula. So n is log delta x over e over log 2. I have delta x, which is 150. The error desired is 0.01. So I get that n equal to 13.87. But of course, you know that the number of iterations should be an integer. So I will just select the integer that is just higher than 13.87, which is 14. So I need at least 14 iterations to be able to reach the absolute error desired. Okay? Any question on this? Okay. Now we will see some properties of convergence of the bisection method. Okay. The first property, if I take this same example here, I am solving for this function, and I do several iterations. I can see that if I draw the behavior of epsilon absolute, it is continuously decreasing. Epsilon approximate, the approximate error. Okay, it's always decreasing. This is called monotonic convergence. Okay, so if we look at the approximate error, it is decreasing in a monotonic way, while if we look at the true error, it's as an overall trend, it's decreasing. But if I look locally, it can decrease, then increase a little bit, then decrease and increase a little bit. We will see why. We will explain this. But what is interesting here is that epsilon approximate, the approximate relative error, is always larger than epsilon true. And this is very good for us because epsilon a will always decrease. And if we ensure that epsilon a is smaller than a certain stopping criterion, we can be sure that epsilon true will also be smaller than this value. So it's enough for us to check for epsilon approximate, for the approximate relative error. Now, why we have this behavior? Why epsilon true can do oscillation? To understand this, I will give you a simple example. If you take a certain bracket and your root is very close to the center, so from the first iteration you do, when you divide your bracket into two, you are already very close to the solution. So if you compute epsilon true, it will give you a very small result. Now, when you do the second iteration, okay, you will say now my root should be between this part and the upper end, because these two will have opposite f. So now your new estimate will be here. So what happens then, that your true error will increase because you were more close to the exact value in the first step than in the second. This is due to the fact that your exact solution can be anywhere in the interval. So when your exact solution is close to the center, this will give you a very close approximation for it, but after you will be away a little bit from it, and you should continue to do several iterations to go back to your root, to be close to your root. This will cause sometimes oscillation in your true error because of the relative position of the true root compared to the bracket. It can be at the middle of the bracket, then you can be very close to the root, but in the next iteration, it will be farther from the center, so it will give you a little bit larger true error. But if you observe the general trend, in general, okay, it will be decreasing. Now, the maximum deviation between the approximate and the true error will be when you have your root close to the center. While if your root is close to the end, to one of the two brackets, then the true error will be close to the approximate error. Okay, because in this case, you know that we will see why the approximate error is always larger than epsilon true. Because look, if you just consider the initial bracket I am considering, okay, once you divide by 2, okay, now you are in case the length of your interval was a, okay, now the new value for your interval is a over 2, okay. So already for the approximate error, okay, what will happen is each time you are reducing the interval of the approximate error by 2, because if now let's say xi, sorry, I had some connection issues. Do you hear me again now?
Yes, doctor.
Yes.
Okay. Okay. So we were talking here, we were explaining why the approximate error is always larger than the true error. Because consider that, okay, I have at a certain stage, let's say this is the position, this is my x estimate of the root at I iteration, okay. Now, in case here the interval, the length of this interval was a, okay. Now when you do an estimate for xi plus 1, it will be from this side or from this side, okay. But anyway, you will have that the relative difference between xi and xi plus 1 okay, will be a over 4, because already if your initial, let's say at a certain step you have a length a, you have, when you do the estimate at xi, you will reduce the length of your bracket to a over 2, and at the next step, okay, you can reduce it to a over 4, okay. So now when you do the approximate error, let's say when you do delta x between xi and xi plus 1, it's of the order of a over 4, okay. While if you want to compare with the true value, if you know the exact value, okay, so you do xi plus 1 minus the exact value, the difference should of course be smaller than a over 4, because the root is inside the interval. It cannot be outside of it to have a difference higher than a over 4. So always, this is why, because delta x in the approximate error will always be larger than delta x in the true error, okay, then the approximate error will be always larger than the true error. And I can benefit from this in saying that even if my epsilon true is not monotonic, but epsilon a is monotonic and always larger than epsilon true, so it's enough for me to observe how epsilon approximate is changing, okay. And but I can say that epsilon approximate is monotonic, but epsilon true is not. And in general, when we talk about the method, we refer to epsilon true, because epsilon true is not monotonic. Then we say that the bisection method is not monotonic, okay. But of course it will lead, I will be able to find a final solution, because at the general trend is a decreasing error, and the approximate error is always larger than epsilon 2, and the approximate error is monotonic, so I can just follow by doing iteration. More I do iterations, lower will be epsilon approximate, and I will be able to reach a convergent solution, okay. So don't confuse between monotonic and convergent. It is convergent, but not monotonic, because as a general trend at the end, I will be closer to the root, okay, in overall, but I might have some fluctuation in epsilon true, but I don't care for that because at the end, I will be, if I do several iterations, I will be close enough to my solution, and I can just look for epsilon approximate because epsilon approximate is larger than epsilon true. So whenever I reach a stopping criterion that is satisfied for epsilon approximate, I can be sure that it will be fine for epsilon. Okay. Anything that is not clear until here? Okay. Now, another
Doctor?
technique, yes?
بس returning to the last slide, إذا
Yes.
كان if we prove that the error is less than the E approximate,
Yes.
يعني ال error تبعنا رح يكون يا أكتر يا lower than the true error.
Yes. يعني أنت مظبوط، يعني أنت بس تكون على طول بما إنه الايرور approximate على طول أكبر من الترو ايرور، يعني أنت بس تحط criterion لل relative approximate error, you can be sure إنه this criterion is also satisfied للtrue error. Okay?
Yes.
هذه الايديا. This is the idea. لأنه إذا أنت وصلت لإبسلون approximate أصغر من 1%، يعني أكيد إبسلون true هتكون أصغر من 1%. Okay? So even إذا الإبسلون true is doing some oscillation, it's not a problem. لأنه at the end it will be always smaller than epsilon a، يعني بالآخر هي حتنزل with a higher number of iteration you will be، يعني أنت تنقول your criteria is 1% وابسلون true عم تطلع وتنزل بس بعدها تحت 1%، it's fine for you even if it's not monotonic, it's conversion.
Yes.
Okay?
Yes.
لأنه ما حتقدر ترجع تطلع فوق ال 1%، ما فيها، لأنه الابسلون approximate على طول بتنزل. اوكي؟ وبكل الأحوال at any instant هي أكبر من epsilon true، يعني لو epsilon true طلعت ونزلت ما حفيها بالآخر تطلع above a certain level، لأنه هي it's bounded by epsilon approximate.
Dear doctor, thank you.
Okay, well. Okay. Now we will introduce the second method to find a root by bracketing technique. هي اسمها false position method. What is the concept? هي very similar لل previous method. The only difference is how to decide on XR. يعني نحن بالbisection method XR he just at the middle of the interval, whatever is the function I am working with. On the other hand, in the false position method, the behavior of the function will affect the root position. How? The idea here is also to start with initial bracket. The only condition هي إنه f of the lower end times f of the upper end يكونوا opposite in sign. This is the case here because f lower is negative while f upper is positive. Now, so this is my initial interval. Now, how to decide on a new interval? Instead of taking XR just at the middle, what is the technique? The technique is to join the 2 points, and then the intersection of the line joining the point with the x-axis هي الroot estimate. So now I can consider that as a first approximation, my first estimate of the root is the intersection between this line and the x-axis. So this is my first approximation. Now the other steps will be exactly like the bisection method. يعني what should I do? I evaluate what is fxr to see if it's positive or negative. Here, for example, it's negative. Because it's negative and f lower is also negative, يعني the root is not between f lower and f at r. It is between xr and x upper. So now my new bracket will be this one, between xr and x upper. So now I will repeat the same procedure. Okay, I will join the line between the 2 points, between this point at xr and the upper point, and the intersection of my line with x-axis will give me the new estimate of the root, this one. And as you can see هيدا الgreen point yellow point who will root. I am very close now to the exact root. Okay, so now this is my new estimate for the root. If I do another iteration, I will be very, very close. If I evaluate f, it's still negative. Because f is still negative and the f at the lower end is positive, then I can say that my root is between xr2, the new estimate for the root. So this is xr2. And because fxr2 is negative while f upper is positive, so the new bracket now is between xr2 and x upper. So now all I have to do is to join again whole 2 points. وطلعوا تقريبا الانترسكشن مع الاكسس is nearly coincident with the root. So I expect that when doing the third iteration I will be very close. So this is xr3, which is very close to the exact root.
Doctor, I did not understand the difference between this method and the previous one.
Okay, the only difference is in estimating the root. Okay, let us try to do the bisection method. If you want to use the bisection method, this is your interval. Okay, you can read, let's say, what's this x lower here? X lower is equal to 0.5. Okay, let's say nearly. And what is x upper? It is 3. If you want to use the bisection method, your first estimate of the root will be 0.5 plus 3 over 2. Okay, so if you are use the bisection method, you can say that xr1 is equal to 0.5 plus 3 over 2, which will give you 1.75. Okay, so you go to your graph. This is 1.75. This is for me xr1 from the bisection method. Okay, from bisection. And then you say, once I get xr1, I evaluate the function. It will be a negative value. So now I can say that my new bracket هتكون between, so new bracket هتكون 175 to 3. Okay, so this is the bisection method. Now if you want to use the false position method, what will be your new bracket? The only difference in the way is in the way of estimating the root. You will not say it's just at the middle of the two. No, the criterion here is different. Here, to find the root, you say I will join the first point here to the end point. Okay, and I will see what is the intersection with the x-axis. How do you do this numerically? It's very simple. I will develop it for you here. Okay, if you want to find numerically what is xr, you say I will call this point x lower, and it's characterized by f lower, and this point is x upper, and it's characterized by f upper. Okay, when you join the straight line between these 2 points, you will get a straight line of equation y equal a slope a times x plus b. Okay, because you are interested in the intersection with the x-axis, the first step you do is to find what is the equation of this line. To find the equation of this line, you say, what is the slope? When I want to find the slope of a linear function, it's very simple. I do delta f over delta x. So the slope a can be calculated as f upper minus f lower over x upper minus x lower. This will give me the slope. Okay, so now I have that the form of my equation is y equal to f upper minus f lower over x upper minus x lower times x plus b. How to find b? You know that to find b, I need just to replace or the coordinates of the lower point or the coordinates of the upper point. Okay, let's say you choose to replace by the coordinates of the upper point. What will be your equation? You will say, I will put instead of y f upper. Okay, So f upper should be equal. I will replace this term by a. This is the slope, okay? I will replace it by small a. So f upper should be equal to small a times x upper plus b. So now I can deduce that what is the value of this constant b? The constant b is equal to f upper minus a times x upper. So now I found exactly what is the equation of this line. And to find xr, the root, what is the method? To find the root, I should find the intersection of this line with x-axis. This corresponds to y equals to what? To y equals to 0. Okay? So now to know what is x of the root, I just have to set y equal to 0. So if I replace in my equation y by 0, what do I get? I get 0 equals to the slope a times x at r. I don't know what is xr. I want to find it. Okay? I want to find what is xr for which I get f equal to 0. So it is the intersection with the x-axis plus b. Now I will replace b by its value. I got that b is fu minus a times xu. So if I replace, I get that 0 should be equal to a times xr plus fu minus a times xu. And this equation will give you what is xr. What is xr? The estimate of xr. xr will be equal to xu minus fu over a. So now you can replace a by its value. A is equal to fu minus fl over xu minus xl. So xr in general, the general form for xr, I will apply it numerically here for you. The general formula for xr is xu minus fu times the inverse of a. The inverse of a is xu minus xl over fu minus fl. So it's times xu minus xl over fu minus fl. So now, if you want to use the false position method, what will be your new interval? I will use this formula to compute xr. Okay? Let us do it in this example. What is x upper? In this example, x upper is 3. Okay? So I will replace, so xr is equal to 3 first, minus. What is f upper? At point 3, I look for f upper, the value of f upper, it's 20. Okay? So it's minus 20 times. Now I do x upper minus x lower. X upper is 3. X lower is 0.5. So I have to do times 3 minus 0.5 over f upper minus f lower. F upper was already I found it from here, from the function. It's 20. Now I should compute f lower. So if I look at my figure here, f lower is nearly minus 10. So it's a minus 10, so it's plus 10. If you find here xr, let's do the calculation. It will be different than xr of the bisection method, because in the bisection method, xr is exactly at the middle, while in this method, it's somewhere between, but not in the middle. Okay? Now, when this method will be of higher advantage? If you look here at your function, okay? When your function is close to linear function, the false position method will do a great job. You know why? Because imagine that your function is nearly linear. If your function is nearly linear, it means that when you join the 2 points by a straight line, you will be very close to the root. Okay? Because if your function was linear, In one iteration, you can get the root. So if I have a linear function, exactly linear, I don't need to do iteration. Just I join the 2 points, and the intersection with axis will give me the root. Of course, we will not give linear linear functions. The linear function is very simple to solve. But just I'm telling you why the false position method will work well for functions close to the linear behavior. Because if the function was linear, the false position method will give me the root in one iteration. Okay, so more my function is close to the linear behavior, it's not deviating a lot from linear behavior, then the false position method will be very fast in convergence. While if I have a highly nonlinear function, so this is an example of a highly nonlinear function. So it depends on the exponent also. So if you work with x to the power 10, etc., it will be highly nonlinear. So if you have a function like this, for example, the false position method will not perform well because the straight line behavior is very far from the behavior of the curve. So if you join here the 2 points like this, you have a large difference between the line and your function. While in the example we have considered here, the behavior of your function is not very far from the linear behavior. This is why it will be good here to use the false position method. And you can, in just 3 iterations, you can get your solution. While maybe in the bisection method, you will need more iterations. Okay? Any question on this? So here, you just have the general procedure. You will see that the general procedure is exactly the same as the procedure in the bisection method. The only difference will be in step 2, in the estimate of the root. Because in the bisection method, the root estimate was not depending on the function. It was just xr equals x upper plus x lower over 2. While here, because we are joining the 2 points of the function and we are finding the intersection with the x-axis, we say that the false position method is function dependent. And the more the function behavior is close to the linear behavior, then the false position method will give a very fast convergence. Okay, so here we demonstrated together in the previous slide that in case of false position method, the estimate of the root is given by the following equation: xr equal xu minus fu times xu minus xl over fu minus fl. This is the only different step. All other steps are the same. So once you compute the root, you should verify if your convergence criterion is satisfied or not. So you should compare xr new with xr old to find the approximate error. In case your criterion of convergence is satisfied, or in case you reach the maximum number of iteration allowed. So sometimes they can give you 2 criterion. They tell you 2 criteria. They tell you, or I reach an approximate error lower than 1%, or I do 10 iterations. The one that you reach before will be the stopping criterion. Okay, so once you have your stopping criterion is satisfied, you can stop iterations and say that this my xr is the estimate I am doing, and I have this approximate error for this computation. Okay, now in case your criterion is not satisfied, then the 4th step is the same. I want to determine a new bracket interval. So for the new interval, it's the same procedure. I evaluate the function at the root estimate, and I compare the sign with f lower. If fr times f lower is negative, this means that my root is between x lower and xr. So I should update now the value of x upper. So I put instead of x upper xr, while I keep xl unchanged. On the other hand, if fr times fl is positive, this means that the root is not between xr and x lower. The root should be between xr and x upper. So my new bracket will be between xr and x upper. So in this case, I will replace x lower by xr, while I will keep x upper unchanged, and then I get my new bracket, and then I will repeat the procedure until reaching the required convergence criteria. Okay?
Doctor,
Yes?
if they specified the number,
Yeah, sorry, can you repeat?
if they specified the number of iterations,
No.
يعني if they said مثلا 4 iterations,
Yes.
we apply the 4 without mentioning the error.
Yes. If they just tell you stop at the fourth iteration, you no need to calculate the error. Okay? Yeah, you have several possibilities of question. They can just tell you you should stop at the fourth iteration. So you do four iteration and you stop. You say my estimate for the fourth iteration is XR equal to this value. They can give you two criteria. They can tell you can stop or when you reach the fourth iteration or when epsilon is smaller than 1%. Then in this case, at each step, you should check for approximate error, okay? In case it's smaller than 1% before the fourth iteration, you stop. In case not, you continue until the fourth iteration. بس وقت توصل على fourth iteration, even if epsilon was not smaller than 1%, you will stop. لأنه الكرايتيريان هو one of these two. بمجرد ما one is satisfied, you will stop. يعني حتى لو على الفورث iteration epsilon أكبر من 1%, you cannot continue. لأنه هن قالوا لك إنه الكرايتيريان is to reach 4 iteration or to reach epsilon smaller than 1%. But if you reach epsilon smaller than 1% before the fourth iteration, you stop كمان. لأنه this is satisfied. يعني to stop, one of the two conditions should be satisfied. وإلا ما إلا معنى يعطوك هيدا الكرايتيريان. اوكي لانه اذا ما راح توقف على الفور يعني الكرايتيريان هو مش النمبر اوف iteration الكرايتيريان هو بس الابروكسيمت error بينما if they put this or this يعني or you do for iteration in case epsilon بعدها ما وصلت ل 1 or اذا وصلت already ل 1 قبل الفورث iteration you stop يعني اذا على stage 3 epsilon smaller than 1% you say no need to continue to the fourth iteration.
Yes, Doctor, clear. Thank you.
Okay. Any other question?
Doctor, you will specify the method that we should use or we will be given the graph حتى نعمل estimation أي أحسن.
Okay, look. In general, I give the method or in case يعني مثلا I can tell you what method is better. So you should look at the function إذا هي linear أو لا إذا close to linear يعني كيف فيك تعرف مثلا من البولينوميال order يعني in case مثلا كانت x to the power 10 يعني it's highly non-linear أكيد bisection method حتكون أحسن. اوكي حتى كمان it depend on the interval you are working on يعني sometimes بدك الجراف اذا بعطيك الجراف يمكن تقدر تشوف اكثر اذا البيهيفير بهذا zone linear او لا اذا قريب على linear او لا. We will do such analysis in next slides. Okay.
Okay, doctor. Thank you.
Any other question? Karen, I didn't understand your question. Are you asking a question?